Hi, I'm Keaton Burns. I'm a research scientist in applied math at MIT. I used to be a postdoc here in CCA. And this is Daniel Lecoanet. He's faculty in applied math at Northwestern. And we're two of the 5 core developers of this code called the Daedalus code, which I think is probably pretty different than a lot of the codes that you guys have heard about so far in the last couple of weeks. So it uses a type of numerical method called the global spectral method. So today we'll go through lots of the details about how those work. It turns out that they're methods that are very powerful for incompressible and low Mach number flows. So in astrophysics, you tend to see these used for things like interior flows inside of stars and planets. But they're a very flexible method, actually. So the Daedalus code is not designed specifically for those types of problems. It's a more generic PDE solver, so it's also used widely in other fields as well. What else? So yeah, so today I guess we're going to go through a few different things, kind of the motivation for why we built the code, the foundations of the numerical methods, and then more in the afternoon, some tutorials and examples on how to use it for different types of problems. But please feel free to interrupt and ask questions along the way here. Okay, so I guess to start off, the main difference between a spectral method and in particular a global spectral method is that the discretization is not done in terms of a numerical grid or control volumes or anything like that. It's done in terms of a set of global basis functions. So we expand solutions in terms of basis functions, and then the whole numerical method is to find the expansion coefficients of the solution in that basis. So again, no grid, we're leaving the grid behind. We're not going to use the term numerical flux again in this talk, so it might be pretty different than before. And this slide is kind of an example of this. So the background image here is a degree 32,000 polynomial that is close to approximating the solution of the incompressible Navier-Stokes equations in a certain regime. So the entire code is about how to get the coefficients of this polynomial in a polynomial basis. Okay, so before we get into the method, I wanted to say just a little bit about the design perspective behind Daedalus as well. I think we were really interested in building a code like that because we had sort of observed that in a lot of areas of computational science and computational astrophysics in particular, the software that you see tends to be really focused on performance, right? People want to run the largest simulations they can, the highest Reynolds numbers, things like that. And often that involves a trade-off, and that tends to be that they also tend to be narrowly focused, right? So they're really only good at maybe a specific set of problems. And if you're interested in doing a multi-physics problem or something, that's different than what the code was designed for, oftentimes it's hard to use those types of codes for those things. So here's just a few examples of codes, and these are all great codes that have done tremendous science, in their niche for sure. But as soon as you take them and you want to solve a different problem, it can be very hard, right? So commonly these codes use low order methods, they use hard-coded equation sets or compiled languages, and they're really difficult to modify, right? It can take months or years just to add like a new type of source term to some of these solvers. And our interests scientifically were sort of spanning astrophysical fluid dynamics, but also geophysical fluid dynamics, different things. We were really interested in developing a model that let us more easily explore different types of fluids problems. And that was sort of hard to do with some of the existing software. So these are all sort of, I say the hammers, right? They're really good at solving specific problems, but hard to modify for different things. And then kind of on the other end of the spectrum is in the applied math world, right? People are really interested in those types of things, right? Developing new methods that are flexible and can solve lots of different types of PDEs. But there you tend to see that they build software that, is just designed around the little test problems they use to write their math papers, right? So they're really interested in solving, the diffusion equation in 1D or something like that, right? And those are good test cases, but often that's too simple, right? And they don't actually take the full step to build like a Navier-Stokes solver or something that can run in multiple dimensions or in parallel. So these codes often, they just don't have the complexity that we want to actually solve large-scale physics problems. And as a result, you sort of have this gap between these two worlds. So these are sort of like the Swiss Army knives, right? They're good at lots of things, but they're not really the right tool for any major job. So if you think of like this sort of space of accuracy and flexibility versus performance and scalability of PDE solvers, I think the domain-specific scientific solvers are sort of up here, right? They're They tend to be low order for specific problems, but very high performance because they want to do high Reynolds numbers flows. And mathematical frameworks are on that side. And the question is really, can we use modern software engineering and also modern mathematical methods today to try to move up towards the upper right of this plot and combine both of these things? And this was always sort of the goal of Daedalus as a project. And I'd say we've sort of kind of started from this direction and moved up, but certainly there's lots of other projects that are trying to go towards this direction from every different starting point. Okay, so again, Daedalus is the code that we've built to try to do this in the context of this particular numerical method, these global spectral methods, which turn out to be, I think, an easy starting point for achieving that because of their modularity and flexibility. So this is the code. We have a website, but in short, really what Daedalus is again, it's not a fluid solver. It's a generic PDE solver. So it's a system that lets you symbolically enter the equations that you want to solve. So here, this is the incompressible Navier-Stokes equations. So U is a vector field here. So this is a momentum equation, incompressibility, and then this is really like a temperature equation for buoyancy. So we just type in those equations, and then what the code does is it produces a spectral solver that solves the model that you enter. So this enables you to really rapidly explore different problems and different geometries. So this is a simulation of Rayleigh Benard convection in a spherical shell. But again, you're not limited to just hydrodynamics. You can solve things like network problems on graphs. So this is the nonlinear Schrodinger equation on some strange network. But in addition to these sort of smaller toy problems that you can run on a laptop, the code also scales up well. So when we do this automated step of taking the equations you enter in and producing a solver, that can be automatically MPI parallelized and really scaled up to do a large-scale fluid simulation. So this is some work by Daniel and Evan Anders that we'll hear more about later. But these are large-scale, three-dimensional, turbulent stellar interior simulations. Okay, so that's sort of, in a nutshell, the point of Daedalus, and then we'll go through the different steps here, how exactly we do this, what basis functions and mathematical methods we use, and then more of the applications that we've worked on with the code. Okay, so before I get into the details of the math, any initial questions? Cool. Okay, so for the next, I guess, well, for the rest of this session, so 45 minutes, we'll talk about kind of just the math behind these numerical methods. So again, they're called global spectral methods. And the basic idea actually just fits in one slide. So that's what's really nice about these methods, is they're very simple and generalizable. So again, the discretization is, instead of thinking about our solution in terms of values in cells or values on points, we think of the variable we want to solve for, u of x, as a function, and we expand it in a finite number of basis functions. So these are continuous in space and global, meaning they span the entire domain that we want to solve on. And then really what we want to solve for is these expansion coefficients, right? Just the numbers in front of each basis function. Okay, so how do we do that? Well, this representation is discrete in the sense that we only have a finite number of basis functions, but it's still continuous in space. So the way we solve a PDE, so say we have a differential equation, LU equals F, here L is some differential operator. Well, we can plug in this expansion, but then this is still continuous in space. So the way we make it discrete, like actually turn it into a matrix to solve on the computer, is by taking projections against another set of what are called test functions. So this bracket notation just means an inner product, and the size here are some potentially different set of basis functions that could be different than the phi's that I use to expand the solution. Those are called the trial functions. So we project against these test functions and say we have n modes in the representation. If we project against n different trial functions, test functions, then we'll get a square matrix that's this L acting on our trial functions projected against our test functions. And now this is like the discrete spectral form of this operator. And it's just a matrix that we can solve to get the solution coefficients. So what's really nice about this process is that it's very adaptable to different problems, right? We didn't say anything about what this equation actually is. For any different PDE that you want to solve, you do the same exact procedure. So that generality is what makes it possible to make a code like Daedalus, which is sort of equation agnostic. So the other nice things about this is that this representation in terms of global basis functions, this gives you in general exponential convergence if your functions are smooth over the entire domain. So that's what makes these methods very powerful for problems in sort of simple geometries and low Mach number flows, right? If we don't have shocks, then the solution is smooth in the sense that it has no discontinuities. And then if we add more and more basis functions here, we get a scheme that doesn't just converge at, say, second order or fourth order, but actually converges exponentially quickly as we increase n. So you get very accurate solutions in those restricted application areas, right, where you have smooth solutions. The main restriction is that this is only possible in simple geometries, right? We need a numerical domain where we can come up with sort of an exponential set of an exponentially converging set of basis functions. So think a Fourier series for a periodic box or something like that. So in general, these methods only work in cubes or spheres or disks, sort of very simple geometries where we can come up with good basis sets like this. In terms of performance, there's two main steps here. So the first is that I sort of like hidden things on the right-hand side here. So we think of this operator L as being a linear operator, and the nonlinear terms in the equation in being on the right-hand side in F. So the two expensive parts of this algorithm are computing F potentially. That ends up usually being the most expensive part. So that requires spectral transforms, and we'll talk about that in more detail later. And then the other part of the algorithm is solving this matrix, right? So we get this discrete version of L based on this inner product. And if that was just a generic dense matrix, that would be slow to solve. So a lot of the art of these methods is to pick the right sets of functions to get exponential convergence, but also to make sure this matrix is structured, like diagonal or banded. It's some type of matrix that we can solve quickly, so that overall the algorithm isn't slowed down by that step. Okay, so of course, there's always details, but in general, this really is like the core algorithm of the spectral method, and that's why it's sort of so powerful and generalizable. So we'll go into now some specific examples of the different basis functions we might pick for different geometries. But any questions just on this basic procedure before that? Okay. Okay, so the classic spectral method is a Fourier method. So this is just for solving a problem on a periodic domain. So Fourier series, our test functions are just complex exponentials, and this gives us exponential convergence for functions that are periodic and smooth. There's also a few other nice properties. So the Fourier series comes with the FFT, so we can quickly go between the Fourier coefficients of a function and its values on a grid, and we'll use that to compute nonlinear terms. And then really the nicest property of the Fourier series is that these Fourier modes are the eigenfunctions of the derivative, right? So if we take any number of derivatives of some Fourier mode and project it against the Fourier mode itself, we just get I times k, or I times the wave number to the power of the derivative, right? So that means if our PDE just has different derivatives in it, then those L matrices that we need to solve in general will be diagonal. So the technical statement is that for any constant coefficient linear differential equation, you'll get a diagonal matrix if you use a Fourier series. So that's a really powerful thing. Obviously, diagonal matrices are trivial to solve. So that makes these methods extremely powerful if you're in a periodic box and, again, have a smooth solution. So otherwise, you lose the advantage here of exponential convergence. So it's always something to keep in mind. Okay, so even if you do have a smooth solution, you might ask whether or not the convergence rate, this exponential convergence rate, matters, right? We know that the classical methods that you've heard about before, finite differences and finite volumes, things like that, if you have a second order, fourth order, sixth order, you can get a high order code. And still, that should work well when you have smooth solutions, right? So you might ask yourself, okay, what's really the trade-off between high order methods like spectral methods and the low order methods in this regime? And to hear more about that, Daniel Lecoanet is going to tell us about his favorite problem, the Kelvin-Helmholtz instability. Okay.
Great, thanks, Keaton. Let's see.
Sorry, can I ask a clarifying question? You talk about smooth solutions. Would you mind expanding what you mean by smooth?
Yeah, so formally, yeah, good question. So formally we mean, okay, you'll get the best case is when your like mathematical solution is infinitely differentiable. So we mean not just no jumps, but no jumps in derivatives also. So this often happens when you solve an elliptic or parabolic type equation. So a solution to the heat equation or something like that will have many smooth derivatives if the forcing is smooth. And this is also a property we tend to see even for turbulent flows at low Mach number. So in the viscous range, when you have dissipation by viscosity, you'll tend to have highly differentiable solutions. So really what we're saying is that if we do a simulation, say, of turbulence, and we have enough resolution to resolve into the viscous dissipation range, then there the solution is highly differentiable. And as we add more modes, then the numerical truncation error we get will fall off exponentially. If you used a lower order method, like a second order, fourth order method, then it would fall off algebraically. So the error would go like n to the -2 or n to the -4. Here, the error actually goes like e to the -n. So for those specific problems, this is really powerful. If your solution was not actually infinitely differentiable, so say it doesn't have a jump, but it has a discontinuity in the first derivative, then the Fourier series itself, the expansion of that solution, the coefficients do not fall off exponentially fast. So then these methods are sort of the same accuracy as you would get from a finite difference case. So they behave similarly, except they're much better in the regime where it's actually very smooth. Yeah.
I was just wondering if there, for a general PDE, is there any way of a priori knowing that you will have smooth solutions underneath?
No.
Yeah, I didn't think so. But.
Yeah, particularly for nonlinear problems, no. I mean, for linear problems, mathematicians work on this. Yeah, but in general, I mean, I would say that this is the behavior you see, right? If you plot a turbulent power spectrum, right, we have like wave number k versus energy. So this is the Fourier space power spectrum, right? If we have some forcing, some process injecting energy at some scale, then we'll get some region like this. This is the forward cascade with the classic Kolmogorov k to the -5/3 fall off. And then at some dissipation range, right, whatever microphysics is actually doing dissipation in your system, beyond that scale, this will go down very quickly. So this is a generic property of turbulent solutions at high enough resolution, for sure. Okay.
So I guess my perspective on this is the simple answer is that if there's no shocks, it's smooth. Okay. And also, I don't believe in shocks. So I think everything's smooth. Okay. So I don't know. Maybe someone disagrees with me, but I guess we're all allowed to have our own opinions. So now I'm going to tell you about my opinion on Kelvin-Helmholtz instability. And the motivation for this was this movie that I found on Phil Hopkins's website comparing Athena to Gizmo, where he shows these two movies, and you can see that there's some, so there's this Kelvin-Helmholtz instability of flow to the left in the red region, flow to the right in the blue region, and then the flow becomes, it goes unstable. You can see this classic cat's eye roll up. And then in the Gizmo simulation, so the two simulations are running with the same resolution, but in the Gizmo case, you get these maybe finer scale structures, and you merge into having two vortices. So there's one big vortex here and another one here, which is kind of split up because of the periodic domain, whereas in Athena, you have four. Okay, and let's see if I can advance the slide. There we go. So on his website, Phil writes, I checked yesterday, it's still here. This was up like 10 years ago that he put this up. So he writes, both develop the instability correctly at the same time, but in Athena, the contact discontinuities must be transported at irregular angles across the cells, which leads to a lot of incorrect excess diffusion. Whereas with Gizmo, these discontinuities can be followed in exquisite detail. Okay, so I thought this was really interesting. So I wanted to try to understand things a bit better. And kind of what we found is that it's not that Gizmo can track discontinuities with exquisite detail. It's that it can track numerical artifacts with exquisite detail. So if you remember yesterday, Mike talked about when you have a finite volume method, you have to pick fluxes. And no matter what fluxes you pick, you always conserve energy. For the fluxes, you could use a random number generator. Okay, and that's basically what's going on in Gizmo. So it's kind of using like a random number generator to generate some of these fluxes, which is producing all those small scale structures. So that's what I'm going to suggest going forward. So how do you know if a simulation is correct? Well, what you should really do is run a simulation, run with double the resolution, and see if you get the same result. And that's something that they didn't do in that test, right? And even better is if you can compare between two codes. If you get the same result with two codes at different resolutions, then you can be pretty confident in your solution. And that's what I'm going to show you, and that's why I'm claiming, based off that, I'm claiming that there's lots of maybe suspicious things going on in that one simulation, the Gizmo simulation that I showed. Okay, now the issue with this problem is that it's a little bit wasteful because you see that there's 4 vortices, so why don't we just look at one? Okay. Okay, so here's just that one vortex. This is in Athena. Okay, so I'll play that again. Okay, so again, we have flow to the right on the top, flow to the left on the bottom. You roll up, and then it kind of becomes a bit turbulent like this. Okay, so I ran this simulation in Athena with a resolution of 2048 by 2048. And then I tried increasing the resolution, and I also tried decreasing the resolution. And these are the 3 cases. So this is the 2048 simulation. Okay, and then now we have a quiz time. You're not allowed to respond if you already know the answer. So the question is, do you think this one's the high resolution, or do you think this one's the high resolution? I guess I'll give you a second to consider. So this one's the medium resolution, 2048, and then one of them is double resolution, 4096. Okay, so we're going to take a poll. Who thinks that this is the high resolution simulation? Okay. Okay, yeah. Okay, 3. Okay, who thinks this is the high resolution simulation? Okay, maybe a few more people. So of course the reason why I asked is that this one, which a priori might look like it's lower resolution, is actually a higher resolution. Okay. Yeah, I only asked trick questions. Okay, so here you can see in Athena, you can increase the resolution from 1024 to 4096 squared, and kind of all these small scale features are starting to go away. And then we tried doing the same thing in Daedalus. So I'm just showing 2048 and 4096, and by eye they're identical. Okay. So this is the power of the spectral method, that in Daedalus at 2048, you get basically the right answer. Okay, this is a very, very accurate representation of the right answer. Okay, whereas you're still not getting it in Athena. Yeah.
In the Daedalus version, are you including explicit viscosity?
Yes. So what we want is to do a problem where as you increase the resolution, you're going to converge point-wise to a given solution, okay? And you might say that's the wrong thing to do. Maybe you should care about the statistics, but I thought it'd be interesting to try to do this.
But just in the Athena, are you also including the explicit viscosity?
Yes, yeah. So we are solving the exact same equations. And another feature is that it's also important to use an initial condition which is well resolved. So I think in some previous works, people had used initial conditions that had discontinuities. So then when you change resolution, your initial condition has actually changed. So in this case, we're using a smooth, infinitely differentiable initial condition. And it develops lots of fine scale structures, okay? But it's always smooth. So there's no shocks here, right? The Mach number, I think, is 0.4. Yeah.
Sorry, you might have already explained this, but I'm relatively used to thinking about resolution in grid codes, but in Daedalus, well, how is that implemented, I guess, just by the domain size or?
That's a great question. And so you'll see in a moment when Keaton shows some of the Daedalus code how to actually set that in Daedalus. But what we mean by resolution is, Keaton pointed out that in the spectral code, you're using an expansion in terms of spectral basis functions. So this is the number of spectral basis functions that we're using. So we're representing this using 2048 Fourier modes in the x direction and in the y direction. Okay, so it's the number of Fourier modes that we're including in the calculation. And we solve for what is the coefficient of each of those Fourier modes. And then if you do a fast Fourier transform, you end up with this. But the code itself is only evolving the coefficients.
You said the Mach number is 0.4, but there's sound speed variation across the domain. So do you mean in the hot phase or in the cold phase?
I don't remember which one.
But it's all subsonic.
It's all subsonic, yes. Yeah.
Ask about the computational time against Daedalus.
Yeah, that's a great question. I think at the same resolution, the Daedalus calculation was 8 times slower. Okay, so this one was 8 times slower than this one. Okay, but it's not getting the right answer yet. Okay, so the next thing that I'm going to show, unless there's more questions, which I'd be happy to answer, is what happens when you increase above the resolution of 4096. But yeah.
Sorry, so just to make sure that I understand, so when you run it over time, this time evolution is only caring about like the coefficients in time. So it's solving the time evolution of each of the coefficients corresponding to the.
Yes.
Okay.
Exactly. Yep. And this of course is just at one time. Yeah. Any other questions? Okay, so now let's try to compare these quantitatively. So what I've done is I take these different images, I subtract them, and then I square the result and integrate. And so that's the L2 error squared, I guess. So I'm going to assume that this resolution is our closest approximation to the true intrinsic solution of this problem, and we've shown in various ways that's a good approximation. Okay? So what we're going to do is that we're going to compare each of these simulations to this one. So this is a plot of the error as a function of time for the low resolution Daedalus simulation in comparison to the high resolution one. And early on, it stays pretty small, but then it starts to increase exponentially. This is due to chaos. So this is like the Lyapunov exponent of the chaotic flow. And then there's some nonlinear saturation at late times. this is what happens in Athena. Okay, so in Athena at low resolution, 1024, you develop some instability here, which causes the errors to grow very quickly. Yeah.
How do you choose an appropriate time step for Daedalus?
Using the CFL criterion that we talked about yesterday, for instance. Yeah. Good question. So when you increase the resolution in Athena, oh yeah.
Sorry, quick follow-up to that. You said using the CFL criterion, but my understanding is that's based on the size of the grid cells. And we don't have a grid here. How do you use that?
Yeah, really good question. So the same analysis that you can use to derive the CFL criterion, you can use the same type of analysis for a spectral method. And I mean, it's possible that maybe it was first derived in that sense. And what you find is that it's no longer the grid spacing, but instead it's the largest wave number that you include. So that's kind of what we think of as the grid resolution.
Okay, that makes sense. Thank you.
Okay, and any other questions? So when you increase the resolution of the Athena simulation, you get the same instability, but seated at lower amplitudes. Every time you increase the resolution by a factor of 2, that instability, which is not supposed to be there, gets seated at an amplitude smaller by a factor of 8. Okay, so the thing that's seating this instability, these numerical errors, are probably due to the reconstruction. We're using the PPM method, which is third order. Overall, the Athena calculation is second order, but the thing that's seating this instability is a third order effect. Okay, so now this is the 4096 calculation. So same story. We went up another factor to 8192. Okay, so in all cases, you get the exact same instability. It's just being seated at lower and lower amplitudes. And then, so it turns out that this, I mean, it's a 2D calculation, but it's kind of high resolution. So, so we wanted to go one higher, but it was going to take like over 1 million CPU hours, which we felt like was maybe a bit of a waste for doing some silly Kelvin-Helmholtz test problem until someone told me that they had computer time that was running out in a month and they didn't know what to do with it. It was like about 1.5 million CPU hours. So I went for it and ran at double resolution again, the 16384 squared, and it turns out that this one is just as accurate as the 2048 in Daedalus. Okay, and I should say that this isn't there's nothing like special about these like coinciding or the level of accuracy of this calculation. I mean, if you did like an intermediate resolution Daedalus calculation, the errors fall. And this is actually, this ratio here turns out to be the resolution of the simulation to the third power, which is indicating that the errors in Daedalus are not due to the spatial resolution, but instead due to the temporal resolution. So we're using a third order accurate time stepper. We could have gotten just as accurate using the same resolution and just taking a smaller time step. Okay. So here, all the errors in Daedalus are due to time stepping, not due to the spatial resolution. Okay, so someone asked about how much time it like the speed comparison. So for this problem, if your goal in life was to run 2D low Mach number Kelvin-Helmholtz instabilities at a Mach number of about 0.4, I'm saying that this Daedalus simulation is 8 times slower than this Athena simulation. When you double the resolution, since it's 2D, but you also have time, it's 8 times slower. So this one and this one are the same amount of time. Okay, but then to get the same accuracy, you need to go 2 more factors of 2 in resolution in Athena. So that's 64 times as expensive in Athena to get the same accuracy in Daedalus. Okay. So if your goal is pointwise accuracy for this problem, spectral methods are definitely going to be more effective than low order finite volume codes. But spectral methods are always best for accuracy. Okay? But that might not be the thing that you're trying to maximize when you're running simulations. So just to show you what this looks like, so this is the high resolution Athena calculation. If you compare it to the Daedalus ones at kind of like these early times, it's almost indistinguishable. And then at later times, you start to develop some differences. So Jim was really excited that this shows that Athena is doing the right thing, right? So all these fine scale structures you might see in Gizmo, those are not supposed to be there. Those are like a numerical artifacts being seeded by grid noise. And he was so happy, I think, that for a recent I think it was his 60th birthday, his students and collaborators got him this little image of the Daedalus versus Athena on comparison of this cage problem. Okay, so I thought that was pretty nice. Okay, so that's all that I wanted to say about this. So I think the point is just that this it hopefully shows you the power of these spectral methods for in terms of accuracy. Yeah.
Question. Maybe I missed that. So you're plotting there the L2 norm of the error. What is the reference against which you are benchmarking the L2 norm?
Yeah, so it's this high resolution Daedalus simulation. And what we showed is that all the other simulations we ran converged to this simulation. Whereas if you thought that maybe this was the more accurate simulation, you don't find that the Daedalus simulations converge to this. Okay. So that's the reason why we think that this is our best estimate of the real intrinsic solution of the PDE.
If you calculate the Daedalus at the 16384 resolution.
Yeah, it'd be even more accurate. Yep, yeah. But the okay, but the thing is that what we showed is that actually, because from this kind of convergence, you can estimate what would be the error of that high resolution simulation, and actually that's much smaller than these errors here. So we think that this is actually a good estimate of the real error. Yeah.
So your solution from Daedalus is in Fourier space, and at the end of the day, you want to show an image.
Mm-hmm.
So you're gonna have to grid just to do the Fourier transform. So is it almost like a waste if you're not gonna show something at ridiculously high resolution in image plane, like going to Fourier modes that have spatial resolution higher than like the pixel that you're going to show the image with in the end? Do you ever go higher than that in practice?
Yeah, I mean it's similar to Athena, right? So I mean I'm not plotting all the pixels in this image, right? But actually running at this resolution is not sufficient to get the right answer.
Right. So, but once you have enough modes in Daedalus to achieve the right answer,
yeah,
you don't need to go higher than that.
Yeah, that's right. So this is like the power of that exponential convergence. That if you're converging exponentially, sometimes going to higher resolution, I mean, it's not helping you very much, right? And that's actually what we found here. That in Daedalus, the largest source of the error is not the spatial resolution; it was time stepping. So if you really wanted an even higher accuracy solution, you shouldn't increase the spatial resolution; just decrease your time step size. Yeah.
Sorry, I just had a question about this the trick question. So I just wanted to clarify because I thought when you have higher resolution, you resolve more instability. So why is it that? Yeah, why?
Yeah. So that's a great question. I mean, that's kind of the thing that's surprising about this. And it turns out that when you're at low resolution, the numerical errors in the code actually seed instabilities that are not supposed to be there. Okay. So, that there are, in the space of initial conditions, you could have picked a different initial condition which produced instabilities that look like this, but that's not the problem we did. Okay. So the reason why it looks good is that your eye can pick out that there is actually a fluid dynamical instability going on here, okay? But it should not be there for this problem. Okay? It's being seeded by grid noise.
Can I just ask a very simple question? When you talk about convergence, how are you judging that? Is it just by eye looking at images like this, or is there some kind of like metric? Oh, I see. Okay, so when the line is close enough. Okay.
Yeah. So yeah. So what do I want to say? So we're calculating the point-wise difference between all of the solutions and then squaring that so it's positive, and integrating. So that's what we're plotting here, and yeah, and we have some estimate of kind of what the size of that error is as a function of time.
Okay, so when it gets to a point where it's small enough for some threshold value.
Yeah.
Okay.
Yep. So actually, I mean, by the end, in all of our cases, at the end, I would say that we don't have a great estimate of what the real solution is because these errors are all pretty large.
Just wondering, with the Athena ones, it looks like they all sort of get saturated around the same level, and I can't tell with the Daedalus ones do they end up saturating at the same spot over time if you let it go further, or does it actually saturate at a lower?
Yeah. So when it's saturating, that's basically because if you look point-wise at any point, the values are wrong, but this red stuff is always red and this blue stuff is always blue. So it's basically saying that kind of all this stuff is wrong. That's the saturation that you're getting. In the Daedalus simulations, and in the high-resolution Athena, I mean, if you look at these three, they look very familiar. They look very similar. But for me, I mean, I've been staring at this for a long time, so I noticed, for instance, that there's like this hook here, which is wrong. But even these are different because here the red connects here, whereas here it doesn't. Okay? Yeah. So I spent like hours like zooming in, looking, see. Okay. So that's why for these it's a bit lower. Yeah. Any other questions before we get, because we haven't said how we actually really run this. So that's what Keaton's going to discuss next. Okay, let's switch it back to Keaton then.
Okay, thanks. So yeah, I guess from my point of view, to summarize, I guess what I would say is this is something to keep in mind, right? So like at the same resolution meaning number of numerical degrees of freedom. So same number of Fourier modes as grid points. The spectral code is slow, right? So people say spectral codes are slow. That's true. It's 10 times at least slower than a finite difference code at the same number of degrees of freedom. But if you're doing a low Mach number problem that should have a smooth solution, the accuracy sort of per degree of freedom is much higher for the high order code, the spectral code. So you can get the same accuracy at much lower resolution. So that's really the regime where these codes are faster overall in time to solution, is when you're saying how much work do I need to do to achieve a certain amount of accuracy, not a certain amount of resolution, which isn't necessarily a good proxy here. Okay, so in the last few minutes here before the coffee break, we'll just summarize kind of the other types of spectral methods besides Fourier methods. They're the classic one, but they have the restriction that they only work in a periodic box. So what if you want to do something besides a periodic box? I forgot I had this slide. Okay, so before we move away from periodic boxes, I'll point out that Yeah, so right, so we have the stack. Spectral codes are slow per degree of freedom, but they're more accurate per degree of freedom. And so for a long time, these are an old numerical method, and for a long time, people said, oh, they're too slow to scale. People are not going to use spectral methods anymore. But still today, the largest turbulence simulations that have ever been done are 3D Fourier spectral simulations. So this is from P.K. Young's group from Georgia Tech. These are the largest published turbulence simulations ever. They ran 18,000 cubed Fourier modes here, which we're using as a proxy for grid points. And it runs simultaneously on 18,000 GPUs. So this is like an insane box, right? It's really hard to even visualize. You have to zoom into some tiny fraction to even see any structure. But these are the largest published simulations. And last year, at a conference, I think they announced they're up to 24,000 cubed now. So if you're in this regime, right, of like simple geometries and smooth solutions, these will just always be the most efficient methods because of this exponential accuracy. And that's why they're still used today at this scale. Also point out real quick, so yeah, we've had a few questions about like grids versus modes. And there's also this word pseudospectral floating around that you might have seen before. And what this really means is this means that it turns out for the nonlinear part of the Navier-Stokes equations, the advection terms, and in general, other nonlinear terms and other PDEs, it's the fastest way to compute those is to use an FFT to take our Fourier modes, go to a grid, so make an image, and then multiply the images together. So that's called the pseudospectral method. So we're solving for the Fourier coefficients, but when it comes time to compute the nonlinear terms in the equation, we use an FFT. And so there's some details about how to do that, maintaining spectral accuracy. This is called aliasing errors. You might have heard of de-aliasing, and that'll come up when we get to the Daedalus code examples. But that's all that people mean when they say pseudospectral as opposed to spectral. Okay, but what about non-periodic boxes? So if you want to move away from that and do still simple geometry, so still boxes, but with, say, boundaries and different boundary conditions, you can use polynomials instead of Fourier series. And the best polynomial series to use is what are called the Chebyshev polynomials. So these are what you get if you take cosine modes and you plot them on the unit cylinder and then project down into the plane. It turns out that this process, this little projection, gives you a set of polynomials from -1 to 1. And these are orthogonal polynomials. They're a good basis set for functions from -1 to 1. And they have all the nice properties of Fourier series sort of through this geometric connection, right? So if I want to solve a problem from -1 to 1, I can sort of think of lifting that problem onto the cylinder and then solving it with Fourier series on the cylinder. And that's exactly the same as using this set of polynomials called the Chebyshev polynomials from -1 to 1. So they give us exponential convergence, and we can use a DCT, a form of the FFT, to go between grid points and the polynomial coefficients quickly, and so on. So these are really the most commonly used orthogonal polynomials. But to make the algorithm fast, it turns out that we need a few different types. So I have one pretty mathy slide on different types of orthogonal polynomials. So the Chebyshev polynomials are a type of a more general class of polynomials, which are called Jacobi polynomials. So these are denoted Pn with these two coefficients alpha and beta. So this is a polynomial of degree n in the variable x. And the alpha beta are parameters that describe different families of polynomials, and they're families that are orthogonal under this weight. So it's just some expression, but not too detailed, it's just here for completeness. So the Chebyshev are like a choice of a certain value of alpha and beta here. And what is interesting about these polynomials is that they're closed under differentiation, right? We sort of said that to make a spectral algorithm sparse, we need to find a basis to project against that gives us a sparse matrix to solve. And these are the ones that have that property. So in particular, if I take a derivative of one of these Jacobi polynomials, so say I take a kth derivative, then what I get is exactly one polynomial back, and it's of a different degree, right? Because if I differentiate a polynomial, its degree goes down. So it's degree n minus k, and it's a different family. So the derivatives of the ABs don't go to AB, they go to A plus K, B plus K. So what that means is that a spectral method using these polynomials will sort of be changing around between different bases here with these different parameters in order to get sparse representations of derivatives. In general, all of these families, though, have those nice properties that they give us, similar to what Fourier series did. Now these give us exponential convergence for smooth functions on the bounded interval from -1 to 1. And there's three important examples that you might have seen before. So first are the Legendre polynomials. So if we take alpha and beta to 0, then this weight factor is just uniform. So these are just the polynomials that are uniform from -1 to 1. And these are important mathematically because they give the best L2 approximations to functions. Chebyshev, as I said, are one of these, and they're the ones you get if you take alpha equals beta equals -1/2. And again, those are good because they come with the fast transform due to this geometric connection to Fourier series. And then finally, we're going to use this identity on the Chebyshev polynomials. So we're going to differentiate those. And the families we get back have a special name. They're called the ultraspherical polynomials. So they have alpha beta equals k -1/2 for ultraspherical of index k. So those will be the basis that is used to represent the kth derivative of Chebyshev polynomials. Okay, so just to kind of show what this gives you now. So this is a simulation I did for my thesis on turbulent enhancement of glacier melting. And so this is a problem, well, to back up. So the general physical setup here is that in places like Greenland, you have glaciers that flow down into the sea through valleys. And where they actually meet the ocean are in these glacial fjords, and you end up with a vertical ice face at the edge of the glacier that's flowing this way into the fjord. And these ice faces can be huge. These can be like kilometer deep fjords. And what we're interested in is how fast does the ice melt where it meets the warm seawater, right? And what happens is the warm water melts the ice, and then that meltwater is fresh and buoyant. So it runs up the glacier and forms a turbulent plume. And really it's the heat transfer across this turbulent boundary layer that controls the melt rate of these glaciers. So we wanted to study this. And so we have like kind of a zoom in simulation of a local patch of this face, but it's clearly not periodic, right? We have ice on one side. So we're going to use a Chebyshev discretization in the horizontal here and put boundary conditions representing the melting ice on the left side of the box here. And then it's sort of a local zoom in. So we're doing periodic vertically on this zoom in box. So there's a Fourier series in Z and then Chebyshev series in X. And I'll just play the movie. So you see this is buoyancy, so sort of like temperature, and then the meltwater fraction. And you can see you get this instability and you get these plumes running up the face of the ice, like we said, sort of mixing in meltwater into the interior. And from this, we can diagnose the melting rate. But obviously this would not be possible with like a doubly periodic box with the Fourier series, right? Because we need this special boundary condition on the left-hand side. But these are really the types of simulations you see. So they're still geometrically simple, right? We're still in a box, but using Chebyshev has let us do maybe more interesting boundary conditions than we could do just with Fourier. Yeah.
Sorry, can you just explain to Keith why we see instabilities between the boundaries?
Yeah, so so the simulation is sort of all in the fluid. So it's just the edge of it that we think is the ice. So what happens is the warm water melts the ice a little bit, right? And then the bit of the ice that melted, so that now is like adding fluid into the ocean, but that is fresh, it has no salt in it, and it's very cold. And it turns out that it ends up being buoyant with respect to the ocean water that's already there. So at these temperatures, it's really salinity that controls the buoyancy of water in the ocean. We normally think of temperature controlling buoyancy, right? Things rise if they're hot and fall if they're cold. But if you add salt to water, it gets more dense. So salty water is dense, fresh water is buoyant. So the fresh water that you add is buoyant, so it wants to flow upwards. So you could just get like a laminar profile of water flowing up, but it's sort of like the Kelvin-Hamilton stability now on its side, where we have this freshwater layer that wants to go up, and we have this static layer here, and that shear interface becomes unstable, and that's what causes these little rolls and triggers turbulence in this flow. Yeah.
can I ask just a very basic question? So what sort of problems, for which problems wouldn't we be able to use periodic boxes? Like, because I understand they're sort of similar to doing a zoom-in simulation, so.
Yeah, well, I guess the obvious, I guess there's two cases. The most obvious one is if you actually have a physical boundary, right? So in this case, we actually want to simulate what happens at this like solid liquid interface. So we have a real boundary condition here, right? Or say you wanted to do an atmospheric simulation and you want to look at the stratification above the ground, right? Like if you have a solid impenetrable boundary, then you don't want just to model that with a periodic fluid that would kind of cover space infinitely. Also, in some cases with a zoom-in simulation, like maybe you do only want to simulate a parcel of a fluid, but if there's like a large scale inhomogeneity, like a background stratification or something like that, that may also break the periodicity, right? So you might say, I want a segment of the atmosphere at a certain level, and that's very different than the atmosphere far above and below. So maybe in some cases then, doing a periodic boundary condition vertically would be bad. Yeah. Yeah.
So you said you had Chebyshev horizontally and Fourier vertically.
Yeah.
Can you have, let's say, Fourier series in arbitrary orientations?
So you can have arbitrary combinations of these, but they're sort of like Cartesian products.
That's
So,
what I'm saying,
yeah.
Like arbitrary.
Yeah, so the standard thing is to have orthogonal things, but you can sometimes put in like stretching or remapping terms to give you like tilted coordinates. That is possible in some cases, but not always. Yeah. Yeah.
Just purely out of curiosity, what are the like physical units for the time scales?
Okay.
It was a long time ago.
Yeah, these are actually not physical units, but nominally this is probably something like a zoom in to about like half a meter of the ice interface. Yeah.
And over like
Vertically, and the total depth here, these range from 100 to 1,000 meters. These can be a kilometer deep or so. Yeah.
and the time scale of this sort of instability and like
Yeah, the time scale for the shear instability here would be, the velocities are relatively low, so this would be like 10-second sort of time scales probably in the simulation units. Yeah. Any other questions? Okay, so this is kind of the type of thing you can do with Chebyshev as opposed to just Fourier, right? So not, still simple geometry, but less simple in terms of the boundary conditions. But what really matters for scaling this up to larger and larger simulations is maintaining the sparsity of those matrices, like we mentioned at the beginning. So just a quick word about that, and the reason I introduced these ultraspherical polynomials is because this is also an area where Daedalus differs from many other spectral codes. So many codes use these two algorithms, which are sort of the classical Chebyshev algorithms. I'm not going to go into tons of detail, but the basic idea is that they actually use the same test and trial functions. So the basis they expand the solution in is Chebyshev, but then they also project against Chebyshev to get their discrete matrices. And it turns out if you do that with a derivative, you get a dense matrix. So differentiating, say like the 10th order polynomial, that gives you a degree 9 polynomial, but it also projects against all the lower odd degree polynomials. So the matrix for that ends up being the sort of dense upper triangular thing, and that's slow to solve. So this limited the scaling and also the numerical conditioning of many other Chebyshev codes. But it turns out that if we use that identity and instead pick our test basis to be these ultraspherical polynomials, we can fix that problem, right? We said if we differentiate Jacobi, we get a different family. So that's exactly what we do now. If we differentiate Chebyshev and project it against the ultraspherical basis, we get a matrix that represents the derivative. It still is upper triangular, right? Because differentiation has to lower the degree, but now it only projects against one other mode in the test basis. So the derivative operator is banded with just one off diagonal band. So this is sort of as close as possible as you can get to Fourier, right? In Fourier, we said these these matrices would be diagonal because the Fourier modes are eigenfunctions of the derivative. And this is sort of as close as you can get, right? In general, we'll get banded matrices for the PDEs you type in. And that ends up being a very powerful thing, because in Daedalus, what that allows you to do is solve coupled systems with implicit solvers very efficiently. Okay, so the three main points of spectral methods to review is that we want spectrally accurate bases that give us rapidly convergent approximations. We want the sparsity in the differential operators, and then we're going to need fast spectral transforms to compute the right-hand sides. One last note before we take a break for coffee. So yeah, on this notion of sparsity and solving coupled systems, I think, has there been any talk about implicit solves so far, or has everyone been talking about explicit schemes? Okay, so if you do explicit solvers, then generally you have a time step restriction, the CFL restriction, that comes from the fastest waves in your system, right? So if we're thinking about compressible hydrodynamics, those are usually sound waves, right? The sound waves move very fast, and so you always have to time step based on how fast sound waves are traveling across the grid. And if you want to use a solver like that to do low Mach number flows, or even in the limit of Mach number going to 0, which is incompressible hydrodynamics, then you end up having to take an insane number of time steps to evolve over any substantial length of time, because the sound crossing time is so fast in your system. So really what's happening is the equation is transitioning from being hyperbolic to parabolic. And so really you have an elliptic solve that is sort of instantaneously adjusting the pressure everywhere in the domain to maintain incompressibility. And to do a solver like that, it's much more efficient to use an implicit solve rather than this explicit version of time marching. But implicit solves mean that we have matrices that sort of couple all of our variables together that we have to solve. And these end up being super dense and very slow to do. But having these banded operators in the spectral system sort of makes this possible. So here I've written incompressible hydrodynamics in 2D. So we have two velocity components and pressure. And I've sort of written it as the system of equations where we have the momentum equations in the top two rows. So these just have advection, diffusion, pressure gradients, and the time evolution of the velocity variables. And then in the last row, we have the incompressibility constraints. So the last row is just div u equals 0. And what Daedalus can do, or sparse spectral methods can do, is they can just solve this system implicitly and directly to enforce incompressibility. So they are implicitly determining pressure as a Lagrange multiplier to enforce this constraint, and they don't need any splitting or pressure boundary conditions or slow acoustic time steps for this system to work. So a solver like this will only be limited by the advective CFL time. You don't have to time step on the acoustic CFL time, so you can take much longer time steps, which actually represent the dynamics of these models. So maintaining sparsity is really a key, and that's kind of the most important part of Daedalus, so that we can do these coupled low Mach number hydrodynamic problems efficiently. Okay, any questions about this, low Mach numbers? And I'll say the same thing sort of extends to other elliptic type operators. So if you want to do MHD, you have to solve div B is 0. That's easy to do in this formulation. If you wanted to do something like self-gravity, you have to solve a Poisson equation for the gravitational potential. That's easy to do implicitly here. So any sort of elliptic type very fast physics ends up being efficient to do in this type of representation.